we are going to see the demonstrator of the energy consumption by a CPU frequency tuning plugin that belongs to the AutoTune project. The aim is to optimize the energy used by the application. The idea behind is to measure the energy when different parameters are applied. These parameters are related to the frequency and some CPU behavior policies, also called the governors. Due to new kernel user access restrictions, the use of some daemons and servers are needed. The demo runs in SuperMOOC, an HPC system that has the ability to use 16 different CPU frequencies and 5 governors. The application used as an example is a sparse linear system equation solver, which is implemented in Fortran called SIPbench. For the demo, we selected 6 frequencies and just one governor, the user space governor, which forces the CPU to work at a certain clock frequency. We configured the plugin to use 2 properties, the energy consumption property, which measures the energy consumed by the cores, the uncore devices, and the memory, and also the AC and DC energy consumed. The second property is the runtime used by the application when a certain DVFS configuration is set. We see here 2 terminals with SuperMOOC. In the first one, we'll run the application instrumented with Periscope, and in the second one, we'll see the output of the energy daemons. We see here the script to submit the application to the compute node. For the demo, we selected a certain compute node. As explained before, we run SIPbench with Periscope tuning for energy consumption. We check if the daemons are working and we submit the script specifying the application to be run. The daemons have received the first request from the application. This request implies the setting of the first configured frequency. The application is now running in the compute node we selected in our submission script. Let's check the results. For that, we need the job ID assigned to our application by the job scheduler. In this case, this number is 290555. As configured, we tune for DVFS. The first scenario is started. It has 2 tuning parameters. The governor set to 4, which means user space, and the frequency set to the first available one, index 0. As explained before, we can see that we have 2 properties and the application is using the configuration specified by the submission script. Let's now check again the results achieved until now. We set the user space governor and 1.2 GHz as clock frequency. Now we see the energy values obtained by the energy daemons. And the runtime of the scenario. As we have results from the daemons, we now know that the application is finished. Let's check the results from this first run. Now the second scenario with ID 1 starts. Periscope will run again the application applying second configured frequency, which is index 3 from the set in this case. We check again the results and see the parameters that are set. Let's jump till the end of the last scenario. We now check that the application has finished. Let's see the results. For each of the scenarios, we see the configured parameters, that is, the governor and the frequency used, and the energy consumed by the application and the runtime. Let's see these results graphically. In terms of energy, we see that the minimum is located at 1.5 GHz, and regarding the runtime, the minimum is located at 2.7 GHz. The least power used when a clock frequency of 1.2 GHz is chosen. It can be seen that the lower frequency we use, the longer it takes the application to finish, and also higher energy consumption. This means we have to balance energy and runtime at the same time. This new parameter is known as energy delay. The best energy consumption according to the runtime is called energy to solution, is located when a clock frequency of 2.7 is set. We have seen that with higher CPU frequencies, the application needs less time to finish. However, it consumes more power. Since power is energy per unit time, the energy delay will be achieved only when the energy and the elapsed time are optimally balanced.